Good afternoon, everybody. Now the second lecture of Lauro Tomio. Thank you, Lauro.
Okay, so let's start now the second part of our lecture 2. In this case, I'll start with new introduction here, universal prediction of weakly bound atomic system from back experiment to ultra-cold chemistry and adiabatic approach. I hope to give some insight about this adiabatic approach for two heavy and one light particle. And after I have atom dimer elastic, dissociation, and atomic exchange reaction, and our conclusion. Okay, let's start again with the film of physics that I presented before.
Paulo, you cannot hear very well.
Okay.
Maybe put the microphone up.
Okay, but maybe this also. No? So, in view of the actual interest in verifying Efimov physics with different mixing of atomic species, so we move our approach to the analysis of this kind of mass imbalanced three-atom system, which, as shown before, can be more easy to identify probably Efimovs. The only problem that we have to have some mixture in to analyze experimentally. So the investigation of the Efimov physics in atomic system have been studied by several groups. One of the focus have been in the past the helium-4 trimer, which was suggested having the unexcited Efimov state by Cornelius and Glockel in Journal of Chemical Physics in 1986. The relevance of these theoretical studies with helium-4 came more recently with the reported observation of Efimov state by Kunitsky and Toll in a Science in 2015. This study with helium trimer have a long history, at least between the theoreticians, with realistic calculations also being performed by the group of Dubna, Kolganov, Motovilo, and Sofiano. Sofiano was from South Africa. And after they have also some kind of a review in physical particle nuclear about that. I put at least 3 citations here that one can trace them. So that's the title that Cornelius and Glock at that time. See, if exists for 3 helium-4 atoms. This was a study done by the thesis of Cornelius, I guess, at that time. So the system of 3 helium-4 atoms interacted through the intermolecular potential, name of this artifact, and with helium-2. It's a group there that created this potential. No? It's solved for molecular system, and also for helium in particular. No? It's solved exactly within the Faddeev scheme. So they found the trimer as 2 bound states with energy minus 0.11 Kelvin, and another is 10 to the minus 2, there, I think 0.16. Yeah. Where the excited state shows the property of an Efimov state. It is overrun by the 2-body fragmentation after they say, so they have some analysis there, but they made a precise calculation on that. Okay. So weakly bound 3-body system near unitarity. As considered the 3-atom bound in the scaling limit, the first work of our group goes back to 1999 also, in a rapid communication that I published with Tobias also and Delphine Amorim, Physics Review A, which was also complemented by a study with the 3 helium in the scaling limit, published in the Field Body System. This work came as a natural extension of a previous one, in which we have considered 3-body hollow nuclei. So an extension from Physics Review C that we have considered nuclear case, now to atomic physics. This is the scaling function that we got at that time. In that analysis for different mass, we concentrate also in one case that we have equal mass that helium-4 trimer. This curve here, as you can read in this side here, is B3n plus 1 minus B3 minus B2, sorry, the 2-body bound here, and this is the excited state, and this is B2 divided by B3n. N means ground state, excited state, and so on. You can take n equals 0, 1, so the ground state should be n equals 0. But all of them follows theoretically on this curve here. Né? So all the Efimov states are here. They are collapsed just in one curve when plotted in this way. Né? So we take the B3n as a scale here to become a dimensionless. And that I take a square root of this also in this scale here, in both sides. Né? So comparing the scaling limit, that's a solid line calculation, with realistic calculation for the helium 4 times. Suppose the realistic calculation with some kind of more sophisticated interaction. No? That at that time there are a few ones. Results are for n equals 0, for an interaction in the S wave, empty boxes there, and S plus D waves, crossed circles. And for n plus 1 also is there. So if you take the next state, also following the same curving principle. No? So you can see here that as you approach more to the exact unitary limit, when B2 equals 0, the points that we have, the realistic, doesn't matter. Our zero range approach also can follow exactly the same here. And here it is just a small spread that do the same range correction that should appear. So I'm going to talk about universal prediction there. So weakly bound excited state, we have studied after with helium-2 dimer with the lithium-7 molecule, motivated by this study with mixed atom configuration, and considering the available data of weakly bound 2 and 3 body system, because we need at least the 2 body already experimentally or from another kind of calculation more considered more realistic, containing 2 helium atoms. We provide a study considering 3 atomic bound molecular system with helium dimer together with 2 possible isotopes of lithium, lithium-6 and 7, and also with sodium-23. So in this work published in Journal of Chemical Physics, we have clearly predicted that this system in this dimer with the lithium-7 molecular system supports an excited state with binding energy close to 2.31 millikelvin. Oh, sorry. Now here are our motivation also for this kind of study, because that was done in case of bound states that we have. But now we are looking for experiment with atom dimer. And this is, I'm showing just one paper that appears in 2010, ultra cold chemistry. It's more just showing how can be realizable this kind of experience. So, okay. So you have, for example, a collision here. Comes this dimer here, collide with this atom here, and after you have an exchange of particles. So these are the first direct observation of an exchange process in quantum gases. Made in control in quantum gas, open up a new avenue to study chemical processes. These are by the group of Grimm's research at the Austrian Institute of Quantum Optics and Quantum Information. They succeed in directly observe chemical exchange reaction in an ultra-cold sample of cesium atoms and flashback molecules. This flashback because they construct this using the flashback resonance techniques. No? They report this in a physics review letter at that time. No? And these are some more information that one can find also in this reference. As I'm leaving also this here also, if people want to give more, get more details, should go to this reference. This is another paper that appears by experimentalists about collision resonance between ultra-cold atom and molecule visualized for the first time. Okay? So these are an illustration of magnetically tunable flashback resonances in ultra-cold atom-molecular collision. So these are by a group of Chinese, I think. These are Wang Yang and the observation of magnetically tunable flashback resonance in ultra-cold cesium-potassium and potassium collision in science. So this is one paper that we did at that time. I have to go to give more detail about this discrete scaling in atom-molecular collision. So the problem Efimov discrete scaling in an atom-molecular collision. So the discrete Efimov scaling behavior, well known in the low energy spectrum of three-body bounded system for large scattering lengths, is identified in the energy dependence of an atom-molecular elastic cross-section in a mass imbalanced system. That happens in the collision of heavy atom with mass mh here, with a weakly bound dimer formed by the heavy atom and a lighter one. So it's similar as show that experimental case. Approaching the heavy light unitary limit, the S-wave elastic cross-sections will present a sequence of zeros or minima at collision energies, following closely the Efimov geometrical law. So our result obtained with Faddeev calculation was supplemented by a Born-Oppenheimer analysis, opening a perspective of detecting the discrete scaling behavior from low energy scattering data, which is timely in view of the ongoing experiment with ultra-cold binary mixture having strong mass asymmetries, such as lithium, cesium, lithium, ytterbium. Ytterbium is a mass very much different of lithium. So one can do this kind of experiments there. Yeah. So, and our analysis can serve for that also. Can be. So, to start here, because we did also this calculation using Faddeev, three-body calculation, but one can make a better analysis, more simplified here, using a adiabatic approach for two heavy and one light particle. This was done long time ago already by Fonseca, Reddish, and Shanley. They did long time ago this case of bound state. So we are doing, here I have put in this transparency all the data that we have here of this Born-Oppenheimer approximation in case of bound state, and after we extend to scattering also. This is, what is the purpose? This show that inverse square interaction emerges in the low energy three-body problem. We consider two identical heavy particles, 1 and 2, with equal mass m, with the third particle having mass much smaller than this m. From the corresponding coordinates, R1, R2, and 3, by introducing the relative ones. The big R is the distance between the two heavy here, and the hairy is the third particle in the center of mass, the other two, as well as taking the m much larger than m in units h squared equal to m plus equal 1. So we can write the three-body Schrödinger equation in this format here. Okay. So this is for the movement of this correspond to this heavy and heavy particles, and this is for the third particle, and these are the two-body potential that we have now. So these are mass factor that we start mu and nu here now, are the interaction between the particles J and K. As the heavy particles are very slow in comparison with the light particle, we apply the Born-Oppenheimer approximation by decomposing the wave function in this format. So we separate these two coordinates in one as a function of r, and the other a function of big R. So it's better to include this as a parameter, because you are freezing the movement of this heavy particle and taking the other first. So why I put it in this way instead of put as a function of, where R is a parameter. So in this way, the solution of the equation for the light heavy particle will provide the adiabatic potential effectiveness, this one, for the two heavy particles. The coupled system so is given by this system here. So once you have this here, for example, you obtain this energy here, and you can use this for this. So it becomes almost analytical, almost this kind of approach. So at least this one can find also in other place here, and can be a good exercise also to repeat this for the students, because it's quite simple also. So the asymptotic behavior here is not affected by V3R. So in that case, to simplify, we put equal 0 this. So it's just a shift that we can have. For the light-heavy particles, one can take short-wave separable interaction with V1 and V2 having the operator form as operator form as lambda and form factor G. So the light-heavy particle system, which can easily be solved in momentum space by considering Yamaguchi form factor of this format here. Sorry, here is the inverse. It should be a -1 here also in this form factor. It is assumed a shallow bound state with this two-body bound state between alpha and beta. It means between the heavy and the other particle, because the two alpha I can say for the heavy particle. So these are the scattering length of the light-heavy scattering length. The scattering length for the two-body subsystem is assumed to be infinite. So that is the way that one can solve the bound state case that is also solved there in Red, Shanley, Fonseca, Born-Oppenheimer approximation. So this ER you can write in that way also here. And after some transformation, that equation end up with this format here, that this solution in the limit of A going to infinite leads to this equation here. So this equation is a solution of this where A is 0.567. So it's giving some analytical. So the expression for Capel can also be fitted by considering arbitrary values of A, which will give us this format, more general here. Okay? Where C equals 0.185. With this, the effective expression is given by that one. So we'll satisfy both limits in this case with R much smaller than A and R much larger than A. The radial equation for the two heavy now becomes in this format with 1 by R squared here. That's exactly the 1 by R squared as done by Efimov. But one has to remember the following. Efimov already said before that 1 by R, but you have done that in hyperspherical coordinates for three identical particles. So why Fonseca has this idea, Fonseca, Red, and Shelley, to calculate for two heavy and one light, because this can come as an analytical solution. So here for a radial potential, where lambda is dimensional, the system has no bound state for lambda larger than -1 divided by 4. And there's an anomalous value for this value -1 by 4, due to the singularity at R going to 0. There is no lower limit in the energy spectrum, which requires a regularization such that R should be larger than some cutoff there, radial cutoff. Therefore, for a boundary condition, we fix the wave function at R equal RC. So important to note that the geometric scale property is independent of the value of the RC. So the equation 7 ends up with this format here, and where this SA here is this expression that now depends on the mass ratio here also. And this decay is the three-body energy. So here we use the definition SA corresponding to exact numerical factor, usually defined as S0 in the case of identical mass. In the case of Efimov, many people use this S0. But in that case, I'm trying to generalize this. So let us check now with different mass. Check the numerical values obtaining for a few values of M larger than M, in comparison with the values of S0 given by Bratton and Hammer in physical reports. In physical reports, they did exactly calculation also for S0. Now I'm doing just in case of the using this Born-Oppenheimer approximation. So here is a values here that I have for different mass ratio m small divided by m larger, 0.1 till 0.001. So you see that S0 is the exact numerical for each case here in the second line. SA, or I can put in terms of the exponential, or the exponential, but it's similar, it's the same. I should compare this first line with the second line. From here you see the difference for this mass ratio. But this difference is going to be decreasing, and when 0.01 at 1 centésimo, it becomes 3.98 and 0.06, almost very similar at least. And if I go more close to the zero this is going to be almost exact. No? So for the case of bound state with E3 equal minus B3, the solutions are given by the zeros of modified Bessel function of the third kind with pure imaginary order given by this expression for the wave function here. As the wave function must be zero at the boundary condition, where R equals RC, this is satisfied by the discrete values of kappa equal kappa n, where this function here is zero, emerging the geometric scaling in the spectrum. This is a kind of Bessel function here. Okay. These are the ratio that we have between the state and given this by these values here. No? In the scattering case, when E3 is equal to this factor here, the solution of equation 8, let me go back here, this equation here, 8 here, can be found in the online also. Wolfram at that time is found here. Now. It's a bit more tricky, but you can find also and solve analytically this with some Bessel function of the other kind here. These are the solution, general solution, 11, where C1 and C2 are arbitrary constant, which can be given by the normalization of the wave function and continuity of the logarithm derivative. First, the ratio C2, C1 can be given by the condition that UR is zero at some R equal 1. Next, we fix the condition for the continuity of the logarithm derivative. So with Z defined in this way, just for this expression, we have the following expression to obtain the S wave phase shifts. Okay. This is the form that comes the solution where Z is Ka. So here we should note that the continuity of the logarithm of the wave function was done such that an error is expected in the result because of we have used R much smaller than A in the expansion for equation 6. In order to improve this approximation, our effective potential will include a Coulomb-like interaction with equation 8 being replaced by this form that was done by some fitting there that we have taken the solution, and after you can improve this term here by a fit. In our approximation should be valid not only for R much smaller than A, but also for R of the order of A. We need to just adjust the potential by a fitting in this case. In case of a fitting, valid till R equal around 3A, we have this G here, this function here of this format here. However, this third term of Gi is relevant to fitting the effective potential for large values of such can be ignored as it is independent of R and proportional to 1 by R squared. Portanto, it is better to improve the approximation for smaller values of R with almost exact values of R by A, 0 to 0.5 and 1. This can be done in this way. Okay. So this will take some fitting. So in that case, we can improve also this expression here. These are some details that we have about the solution of this. We take from Whittaker function of that for the U. Came to this format. And here are the solution in terms of C1 and C2. The components we are in terms of the same function M, we can use this relation this relation that also found that about this function that we have. So I can jump this part here, that one can go more slowly by looking for a slide in future or by trying to do themselves with mathematics can be done this. So a diabatic approach for two heavy and one light. I have S0 equals this format here, UDR minus KA plus theta, cotangent of delta 0 is given by this expression, cotangent theta is given by this expression. Portanto, the zeros of 1 divided by K cota delta are given by this equation here. Okay? So in this case, we can, by using a diabatic, can compare with the exact calculation that we have. So in our approach, we compute the S-wave phase shifts by using the three-body Faddeev formalism with zero and short-range interaction, as well as by considering that kind of approach with Born-Oppenheimer approximation. The real part of the S-wave phase shift shows zeros, and K cota delta shows a sequence of poles for colliding, which tend to follow the Efimov geometrical scale. Finally, the scattering, observe S-wave phase shifts, cross-section, and absorption parameter are obtained by using the on-shell scattering amplitudes. That's given by this expression where this SA here, you have this parameter, also the Atmo, absorption parameter, and this is the cross-section, the differential cross-section. Where S alpha is the scattering matrix for the elastic S-wave channel, and N usually is much smaller than 1, is the absorption parameter. And this is what we have obtained in our calculation in one limit where the zero range interaction, if you take, you have this in blue here. No? For 0.012, it means that B2 is 0.012 times B3, our scale. No? And for a Gaussian potential, there is a small shift that we have there of this value here for 0.0012 here. It's a bit, 110 is smaller than they found. To have the same kind of approach. So the S-wave cross-section is shown as a function of the energy collision for zero-range blue solid lines and finite-range Gaussian red dashed line potential for fixed mass ratio. The mass ratio is 0.01. So 1/100 of the one of the other, and gives the two-body energy. B2G is a factor smaller than B2 to keep both results close to the unitary limit, because the idea is to go more close to the unitary limit. So this is for these values of A. So we explore a bit more this part here. So the discrete scale in atom molecule is results obtained for sigma in arbitrary unit as a function of the collision energy in units of V3 for three values of the alpha beta binding energy, it means the dimer binding energy, with alpha beta dimer divided by B3 is at 0.01. I'm going to show you in the next transparency solid blue lines. 0.03 is dot dashed red line, is 0.05 for dashed black lines, given in the next panel. So each panel is for a given fixed value of the mass ratio. Here, I hope it's clear there now. Okay. So here the mass ratio is here. A is 0.01, go to 0.08. So you can see that with the mass ratio of this order, you can have a sequence of zero that you can compare, I think, very close to the Efimov limit here. But these, remember, that are in the scattering case, no? For the zeros of K cot delta. No? Now, if you go increasing, it goes slowly disappearing this. So here you can see 0.04, you have only two minimums here, and so on here. And 0.08, it is just one that we have. So you have to go to really very small energy to see this behavior more clearly. This is repeating for A 0.01, that we improve here, with this mass factor here, 0.01, and the two-body divided by 3 is also 0.01, the energy. Here, a comparison, direct comparison in this scaling function that we have for S0. This is a scaling function known for the bound state that we have. As you increase this M alpha divided by M beta, the large one divided by the second one. Or it can be larger or smaller because you are from 0 to 2 here. But the scattering part is just this part here. So just for comparison, that is try to tend at least in the Efimov lines that we have for bound state, what we have in the scattering. So the ratio between the scattering energy corresponds to the position of the zeros of the cross-section are shown with blue bullets there in the same plot already verified by the Efimov spectrum when varying the mass ratio. Here are calculations that are done also numerically, this part here, all this with different values of the two-body divided by three-body energies here for this mass ratio. And now here put the large divided by the lower, so it gives 100. Okay. And here are the calculations done by Born-Oppenheimer approximation. The scattering done by Born-Oppenheimer approximation. What happened here that we are done first this calculation here, and we note a strange thing because the Efimov limit expected should be here for this mass ratio, where this dashed line. So we are expecting this curve should come like this, in this way. But instead of this, it passed through here, becomes smaller. So we are curious because of the numerical calculation that we have done, how precise should be. So this Born-Oppenheimer approximation helps us just to analyze this kind of minimum that is appearing. Because you see, also the Born-Oppenheimer, it crosses here and after converges to this point. Unfortunately, numerically, there is some limitation also for us to go to so much the limit, but one can try to improve also this. So there's the adiabatic, blue dashed curve, and zero range for the F calculation, symbol shown inside, and with this mass ratio scaling plot, with the ratio between consecutive energy poles of K cot delta. K squared, given by this term here, defined in this way, and this is the scattering length of a heavy light particle multiplied by K. So in conclusion, we suggest as the best possible situation to probe the Efimov discrete scale in the continuum to consider the atom molecular scattering with the large mass asymmetry through cold collision, which are now feasible considering some experiments shown before. So the challenge in this experiment should be to control the scattering length towards the large values and then observe the cross-section minimum at geometrically spaced colliding energy. So this is another work that we did at the time with the scattering of helium, cold helium-4, with helium-4 and lithium and sodium, lithium-6 and sodium that I mentioned before. So we predict in this case for S-wave elastic cross-section, sigma, for low-energy atom-molecular collision with kinetic energy at around from up to 40 millikelvin for helium-4 collision with weakly bound the atomic molecules formed by helium-4 with one of these three here. So our scattering calculation were performed by using diatomic and triatomic molecular binding energy obtained from several available realistic models. There one can see from the reference from where comes many calculations that are done with and also are compared after with the normalized zero range. These are can show here, for example, with the lithium-7. Lithium-7, for you can see here, the B3, the value is this here, 79, and this is the helium, alpha, so the 2 helium is 1.31, it's well known, this value, here also the same. And here is one is zero range, and the other is finite range with the Gaussian there, calculation. And these are the minimum appearing some of them, depending on the two-body binding that we are considering. Okay? These are the two-body binding that you can see here, and if you go here increasing, you have this curve here, and after you can see you went to 20 here, 20 millikelvin. Yeah, here. And that's the absorption also parameter that we have there. Okay? To calculate this, we delete 7. Let me see, it's a finite range and zero range here. Zero range is in the left side. No? So you see, there is some range effect that you can see moving to the left. No? Or if I say zero range, move to the right. No? Here is the cross-section directly that you can see also for very different kind of potential models. These are the potential models that we have, A1 to A8. I'm not giving all the details of these potentials here, but one can take from that reference that I showed just before, where we have all these models. Because I'm also going to talk about 2 specific models that we have there. These are zero range and that's finite range, the difference that we can see here. So 8 models that's comparing. And this we have 4 models being compared with helium going to helium sodium. There is this interesting minimum here that we have, finite range, and with zero range, almost similar as the position. This other table depends on the potential, they move a bit. We have 4 models, potential models. And here are the absorption parameters also. So these are the main for the models that we have. Let me see if that's for lithium 6 and lithium 7, and this is for sodium, for model. So now I jump to atom dimer, elastic dissociation, and atom exchange reaction. So this is kind of a reaction that we put more in the language of the molecular chemical physics. Is an illustration of what I have. The atom dimer reaction. For each panel, the entrance channel is in the left side, with the exit channel in the right side. I mean, left and right. Here is the elastic. It means that the dimer is not destroyed. Okay? It keeps going on. And here, a dimer can be formed in this way or in this way. Okay? The 2 identical particles or the different particles. And here I take the same case here, but complete dissociation. And in this case, there's exchange. As I have shown before, one experiment is doing this way. So exchanging the atoms here, this with this. And one is appearing here and becomes here. Okay. And this is when I have 2 identical. So every condition here we have tested. Assuming the helium-4 beta is more bound than helium-2, the dimer of the 2 helium, the atomic exchange reaction is endothermic in the upper right panel and exothermic in the lower right one. So it depends on the binding energy of the dimer. If you are releasing energy or need more energy to become. So if you are releasing energy, so it will be exothermic. So the atom dimer exchange and dissociation reaction are predicted for different combinations of these 2 helium atoms and the alkaline species, lithiums and sodium. We use the 3-body formalism. The helium, of course, the choosing of this is because of the available data that we have for all these systems, or some experiments like helium, and also numerical calculation with other realistic calculation. So we interpret our results also in the light of the ephemeral physics, mean very low energy, which supports this model independence. Because to apply our model, use zero range, we have to go to very low energy usually. So these are the Faddeev coupled formalism. This, I think, Tobias also gave already something about the formalism also in this talk, so one can also go to it just to see. But here I put in the basic that we have, that we have the coupled equation for the S wave, and these are K2 and K1 here, and the other the wave function that we have here, and K1 and K2 are the appropriate moment space kernel, which are explicitly given according to the kind of form factor for the two-body interaction. These are the final equation, coupled equation that becomes, because I'm considering all the situations here for the equation, for the scattering. So from the scattering amplitudes, we can obtain the cross-section. For alpha colliding alpha beta, we have this elastic scattering. Okay. And exchange reaction for this comes in this way also. When we have alpha going to alpha beta, cross-section expression. That can be easily obtained in this format of this cross-section. For the scattering of particles beta by the alpha now is bound here, subsystem, the corresponding cross-section elastic is this one here, and these are the exchange case. It's this format. So the elastic reaction rate is given by the corresponding product of the elastic cross-section with the velocity here, such that we can transform these values that we have here for this cross-section as in some paper that we saw here that the chemical prefers sometimes to use these quantities, these observables. So, for the reaction cross-section. So we transform this for the case of elastic, and anomalous the atom exchange reaction rate can be defined according to the process that we have. Alpha going to alpha beta, alpha to alpha beta going to beta alpha alpha, or beta plus alpha alpha going to alpha plus alpha beta, which is given in this form, the exchange. The third possible process refers to dissociation process, possible for energies above the three-body continuum. When, for example, we have alpha plus alpha beta going to each particle separated here, alpha plus beta. So it is given by a dissociation, by this form, the cross-section of dissociation. So given the above, in terms of the corresponding cross-section, we define the loss rate coefficient also. But these three are enough to define this K-loss that combine the exchange with dissociation, the summation of two. Refers to the exchange and dissociation or breakup cross-section respectively. So here is by considering the cross-section partial wave corresponding, the reaction rate can be written also in this format here. The composite can be expressed in terms of the non-diagonal S matrix for the elastic and for the atom exchange channel. So here are the elastic, exchange, and dissociation, and the loss here. So some are with the model of the matrix S. So this rate provides the available dimer and trimer binding energies in millikelvin, combining 2 helium-4 with lithium-6, lithium-7, and sodium. The given results for model A1 from SUNO, this reference here, and for A2, other model from U1 and LIN. So the data are more from these two papers. We have, as I showed before, in some previous paper, we have about 8 models that we have considered, but we took the more different one that we had, because they are giving quite discrepant results, at least in some cases. Like, for example, you see helium-4 and lithium-6, this dimer. In the model E1, more recent of June, they say 1.515. But this model, E2, is 0.12. So it's quite different. And this makes difference in the reaction and can also be a sample for others, as prototype for other systems also that we have. Because when you have helium-4, this dimer transfer, but for this in the reaction process with the other particle coming, these are increasing the binding energy, but this decreases in A2. Okay, I jump already to the potential. And these are the corresponding three body for each case. Helium-4 plus lithium-6, plus lithium-7, and sodium. Also considering the available data that I have for A1. For A2, the model A2, I don't have data for this case. You don't have excited. In this, we have some excited also. These are the values. The more fixed is this value, also for sodium, I think it's quite fixed, 28, 98. Everybody uses this value. These are the potential if you want to see how is this helium potential is here, and this helium sodium and helium lithium. But you see the A1 and A2, we plot both for the case of helium lithium. And there's a very, very small difference here that makes that difference that we have in this binding energy, 1.5 to 0.12. That's so I put some inset here just to show this difference. No? So this is a classification of reaction channel. The classification of the reaction channel, we have to consider the bound state that we have the dimer and how it goes after. In the elastic process, it keeps the same, of course. You have this and goes at the end in the same format. But in exchange, you take this as the initial and it comes to 2 atoms of helium and lithium-6. So you remember that A1 and A2 are different because one increase energy and the other, exothermic here, release energy. For one, you need to capture energy to become more bound, the dimer, and the other is releasing energy. So why we classify it as endothermic or exothermic. These are the lithium-6 to helium-2, also going to this format here. These are the models that we have. And now here for colliding particle, the helium, colliding helium lithium-7. The same in this case are all endothermic, both cases here. And the lithium-7 going to 2 atoms of helium, the helium dimer. These are A1 is exothermic, A2 also is exothermic in this case, because you are considering this dimer going to this dimer. In general, this helium is the smaller, except in that A1 case, that as I showed before. Sorry, A2. Here. A2 that we have the only energy, two-body energy that's smaller than the dimer helium is this one. So in the zero-range model, we have the two-body amplitude parameterized by the diatomic binding energy, together with the regularizing momentum parameter fixed by the 3 atomic molecule. For the finite range interaction, we assume a rank 1 separable Yamaguchi. So in one case, I use this or use a constant in case but in that case, I need a regularization for zero range. Where Ij is alpha-alpha or alpha-beta, respectively, for the alpha-alpha or beta-two-body subsystem. So lambda and these parameters refer to the strengths and ranges of the respective two-body interaction. As in the present approach, we consider only bound negative two-body subsystem, the corresponding relations for the strength and the range are given by this expression. Can be extracted there. These are in terms of the K alpha-alpha is just the two-body energy in the mass factor here, and alpha-beta also. These are the parameters in a table for the model 1 and model 2, A2. For gamma and the R and the corresponding scattering length of alpha-beta. In a table for the model potentials. Okay. And these are the 2 helium. Here are the results that I can show for the reaction rates for helium-4 going to helium-4 lithium-6. The zero range is in this side here, and finite range is in this side, using the potential model A1. This you can see, for example, the S wave here, and the other wave, the S wave is the dashed here, and the total is the continuous total wave. And P wave is the red one, and D wave is the blue one. And here are the exchange and losses here. So it's starting at some point depending on the energy of the dimer corresponding here. So the exchange and loss rates for the helium going to helium lithium with model 1 show in this figure that I just show here correspond to endothermic reaction. So this here, the threshold energy in order to open the exchange channel at 0.2 millikelvin with the three-body association 1.5 millikelvin. So the S wave elastic rate is dominant below opening the threshold, attaining values of as large as 10 to the minus 9 centimeter cubic in this unit here, for both zero range and finite range potential. Once the atom exchange channel opens, this system going to this dimer here, exchange to this, the P wave becomes noticeable and right away gives the measured contribution in both the atom exchange and loss rate, even above the dissociation channel. The P wave, so its dominance comes from the well-known one-atom exchange diagram, that which, due to the involved small binding energy, has a pole close to the scattering threshold. Physically, in the exchange process, the incoming helium picks the other one from the helium lithium-6 molecule, and the remaining lithium-6 is moving backwards with respect to the incoming. This interpretation that we have here, helium-40 enhancing the P wave contribution of the reaction process. Here are the results with these are the results with the model A1, and these are with model A2. A2 you see here because there is the endothermic, and this already is exothermic. And the difference here of zero range and finite range, you don't see too much difference in this case here. It's quite similar. But some difference exists in some waves here, the contribution. So the reaction for the helium, lithium-6, zero range, and the left range set of panels using A2 model. And this is when I go to lithium-7, the same, I have, this start at some point because of the kind of reaction that we have, zero here. And here what I notice is there's some minimum that we have for some waves, and this S wave, just some pump here for model A1 in this case. And the model A2, if I want to compare the two models, I can see the difference that we have for the lithium-7. For the two models, you see that the minimum just moving to the left a bit, for this here. And these are with sodium. Sodium is a quite big minimum that was zero here, that goes exactly in this part here for the S wave. As you can see also here in this side with the zero range or with finite range. Only that it goes at different speed, both. So these are the reaction rate with zero range and finite range in the left-right set of panels using the model A1. And this with the model A2. Similarly, we can see also a minimum here, at least. Okay. And these are the reactions that appears only after some point here, the exchange, exchange and loss, that depends on the energies that we have. These are lithium-6, now colliding in the dimer of helium. So the dimer helium is the last bounding that we have of mostly of the system. So why we have all the region here for loss and exchange also in this side here. This for the model A1. We have this with lithium-6, and here with with model A2, lithium-6 again. Here we can compare the one with the other. We see just the behavior is change a little bit, okay? But that remember the kind of model. That lithium-7 model A1, and lithium-7 also model A2, similar. And here for sodium, that we have a sodium colliding the helium. That we have this behavior here for zero range and the finite range behavior. And that S wave that we see here, the what is interesting here is these waves here are larger than this one, the S wave, at this region here. Okay? Their contribution are larger. So this is sodium with helium 2. So they are all the values that we put, all the possible exchange that we had to analyze. So I came to the conclusion with perspective. That are the results that we had for this kind of reaction. So exchange and dissociation rates are predicted for atom dimer system with 2 helium-4 plus lithium-6, lithium-7 sodium. These are chosen one of out in view of previous investigation and laboratory accessibility. Because all this system with helium have been studied by the group of Dubna and by since Glock, and many people start to using helium. And after comes these values that Suno in Japan use this system also. So we have a lot of data to compare. So why we have not chosen other systems? But in principle, we could extend this also to other analysis of other systems. We took advantage of the dimer and trimer binding energies are available from experimental data or from realistic potential model. So only the relevant contributions to low momentum, S, P, and D, were taken into account, considering the fact that we are concerned with low energy, such that we are not expecting to have contribution of higher partial wave. The occurrence of minima in the elastic reaction rates, a minimum is predicted in the S wave elastic reaction rate. That can be of interest experimentally if somebody is going to do that, when considering helium-4 going to helium-sodium, this dimer scattering. These are relevant output as may be possible to be verified. A previous related discussion also is in this paper here in 2018 that we have realized about this system that can be interesting. It's not so close to this FMO of physics, but at least it's something low energy that we have a very something interesting result that can be. So we understand that such minimum is reminiscent of the FMO effect principle, translated to the scattering region with a log periodicity of zeros in the elastic S-wave phase shift in the collision of the atom with a weakly bound dimer. Another interesting property is the presence of a zero dip or a zero in the P wave of some of the elastic channel, elastic rates, which can be seen in the case of helium going to helium-7 or helium going to helium and sodium for energy between 1 and 10 millikelvin. And the range sensitivity. So it was verified that the reaction rate result presents some sensitivity to the potential range. This happens when the effective range are compared to the scattering length, particularly for the case that we are mixed with sodium. However, the bulk values obtained with the zero and finite range potential are similar in principle, supporting the robustness of the prediction when considering weakly bound two-body system. So the perspective, I can say just in 1 minute here. The extension of the approach to ultra-cold treatment to study controlled chemical reaction by means of turning the scattering lengths with flashback resonance. So by applying induced field body force, one could also move the triatomic state, as discussed in this paper by nuclear physics, or here, some time ago, in Progress of Particle of Nuclear Physics, and by another paper here that we published in Physics B, a journal Physics B here. There's a period J here. By manipulation of the aspect ratio of the trap, one can also alter the effective dimensions. This is something else that one could do, but in which the reaction takes place in a continuous way from 3 to 2 dimensions. That's some discussion by some people with Tobias also, Ross, I think, and group of the Jensen have done this, and Bean and Jeffrey also. Therefore, we hope that in the future, not only the interaction can be turned, but also the effective dimension. Yeah. Okay, so that's all. So thanks very much. Thanks for all participants and for their interest. Okay.
Thank you, Lauro. Do you have any questions? Comments? Lauro, could you please go to slide number 42? That's something I want to ask.
What?
Yeah, that's it. So A1 and A2 are two models. And they agree quite well for this helium-sodium system molecule. Were they built using this as input? Because the other values, some of them differ quite a lot, as you said.
Yeah, they are just, we'll say that this case of the dimer and the trimer, but you see the difference are only the trimer, the bound state to the dimer is the same here, no?
Yeah, but even for the dimer, for example, helium-lithium, there's a big difference. Helium.
Yeah, these are big difference.
Yeah.
But the result, at least, are not so sensible. Looks like this. It looks like that we are in quite small energy already, as we noticed also this before. The only thing that this case here, that's a different kind of reaction because of the difference in the energy. But these are probably wrong, I guess, because there are many models that are with other values. We put only this one just to test our model, our way to analyze what happened if we take this smaller than that. Because this is one model given by one. You see this 98, I think.
Yeah.
But
20
and
years.
so
difference, yeah.
but the three body here is a bit different. But we can reanalyze that because some time ago that I can see again.
Yeah.
Because there's, and also one thing that you can see all these results in terms of cross-section, if you prefer, because cross-section is there also. We put in that way because we saw some experimental people of physical chemistry putting this calculation in terms of the reaction rates. So we choose this format for the output.
Thanks.
Okay.
Any more questions?
Okay, Professor Tomio, thank you for your talking. I like it too much.
Okay.
And I have one question about the zero range methodology you use it to calculate for the properties, for example, the binding energy of the helium or something like that, the zero range model. And the question is, did you have some divergence in the calculation of these energies in the zero range model? And if you have some divergence in the calculation of the energy, how can you overcome this trouble?
No, we fix the three body. One parameter we have to fix that because we have to regularize that, the zero range. Zero range in the way that put just a constant there, this should be regularized and normalized with one of these parameters. That's why I say the robustness of the result is that they do not depend much. Because if I put something that finite range, it gives some deviation, depends on the place, but not too much. So at least the gross result is already in the zero range calculation, the main part. But of course, if I go far, I go away from the limit that I'm treating. But I have to be considered. I think Tobias also showed this, how to remove this singularity. I put just one equation, but because it was already there before, so I pass through after. But one can consult also the Skolniakov-Maturizan equation and the other equation that Tobias put in also in this transparency. But in this last paper, there is one before that I show here that you can also see the details in one of our papers. How we make this regularization or renormalization, we can say, because when you fix some observable. Okay.
Thank you.
Okay, thank you.
And
Thank you for the
congratulations
question.
for your
No, thank you.
Any more questions?
Ixi, meu Deus.
No? If not, let's thank Lauro again.
Ah,